Now, what we're going to study is chapter 25, section 1. We're going to continue with a look into the nucleus. Okay? So what we're going to do today is look at the general properties of the nucleus, and then we're going to talk about why some nuclei are actually unstable. And the part with the instability is very difficult, and a lot of people have trouble wrapping their heads around it. It does come from the isotopes, yes, and we'll talk more about that when it comes to the number of neutrons, and we'll go into much more detail in a minute. So 25-1, okay? Take a look at the first thing. First, some of this is going to be a review from chemistry. Some of it is a review. So the term nucleon, any part of the nucleus, so a proton and a neutron are the nucleon. That's what makes up the nucleus. So again, the protons and the neutrons are nucleons. They make up the nucleus. That's stuff that should be, already in the memory somewhere. Just recall that information at this point.
If you don't know at all.
If you don't at all, now you know.
If you don't know, now you know.
Guys, you gotta stop. You gotta stop. Come on. The three things that we want to look at here are we're going to look at three symbols. First, come on. It's like the fourth time we've stopped now. The three things that we're going to look at as far as symbols go are A, Z, and N. A, first, is the mass number. And this is seen on the periodic table. On your periodic table, you're going to see two things. You're going to see the mass number over here. Okay, the mass number is the number of the nucleons. So the sum of the protons and the neutrons. So for example, you could have an element like carbon, which has 6 protons, but it could have 6 neutrons. It could also have 8 neutrons. It could have varying amounts of neutrons. And we'll go into detail about what that means in a little. But the mass number is the sum of those two. God bless you. So the protons and the neutrons together make up what you see on the table, which is the mass number. In a minute, I'm going to go over why this on the table you're going to see a lot of the time is a decimal. It's like 27.001. Like, where does that come from? And we'll go into that. The value Z, or the symbol Z, represents the number of protons. Every single element has a fixed number of protons. Boron is 5. Helium is 2. Hydrogen is 1. Elements have a fixed number of protons, and that's how they are named. Okay? So you look on the periodic table, you're going to see all the elements with certain amounts of protons along the way, and that number is not going to change. If an element undergoes something called fission, which we'll talk about later, it can split apart, and then it's two separate elements. So it still, though, breaks into new elements. But any element has a fixed number of protons. Okay? The last part is the neutron number. Capital N is the number of neutrons, and that is not fixed. That is not fixed. That can change. And what we can say from this is simply A equals Z plus N. And this is not a formula I'm going to give you. This is common sense. If I tell you that the mass number is the protons and neutrons together, then here's the proton Z, and here's the neutrons N. Add them up, you get the mass number. Okay, so if you had...
So it's going to be Z.
I'm just calling it, that's what they call it, is Z in the symbols in your book, so I'm using those symbols, okay? But it could be anything, yeah. So, again, the number of protons and neutrons together make up the mass number. So if you have an element like carbon, for example, carbon 612 is carbon with 6 protons and a total of 12 nucleons. So how many neutrons would be there to give a total of 12? 6, because 6 and 6 is 12. But carbon 614 is an isotope of that. And we'll talk in a minute about what that is. So how many neutrons there? 8 neutrons. Still 6 protons, but 8 neutrons. Okay? For example, another one, hydrogen. Hydrogen has isotopes as well. Hydrogen is actually just a proton by itself. There is no neutron. But the minute a neutron is introduced, it becomes... Anybody know what the hydrogen becomes in its isotope form? Not an ion, because it's a neutron, neutrally charged. Ion would be an extra positive or negative charge. It's an isotope, but does anybody know the names of the isotopes for hydrogen? It's deuterium and tritium. Deuterium is adding a neutron and adding 2 neutrons. They have different names they come up with actually eventually, but the idea is that the number of protons is fixed. The number of neutrons can vary. And when the number of neutrons varies, we have isotopes. Okay, Tristan and Emmett.
What is the isotope?
I'm going to get into that in a sec. Hold on. Emmett?
Why is it so hard to move protons compared to neutrons? Because I know electrons are easy to move, and I know protons are fixed inside.
Okay.
Electrons also.
I'm going to answer that question in about 20 minutes. And I'm going to hold off just because to go into that, I want to talk about something else first. We're going to talk about a certain type of force that exists inside a nucleus that is the reason for that. Okay? All right, so to answer your question with isotopes, Tristan, let's go to isotopes. So, again, I said this already, so you don't have to write it, I just said. The number of protons is fixed, but the number of neutrons in a given element can vary. Now, atoms that have different number of elements are called isotopes. So, for example, if you're looking at, and I'm going to use carbon, because carbon is the one that has a lot of examples of isotopes. If you're looking at carbon 612, 6 protons, 6 neutrons, giving a total mass of 12. That's why it's called carbon 612. It is an isotope of carbon 614. Does that make sense? It is an isotope of the other one. You can't say that carbon 612 is an isotope. It's not. It's an isotope of the other one. Together they make up isotopes. So for example, something like, pick an element.
Helium.
Helium. Something like helium. Helium by itself is an element, helium. You can't say helium is an isotope, but you can say that helium has isotopes. And when you compare the different types of helium atoms, some that have more neutrons than others, those are isotopes of each other. Okay? So it's like they don't come in pairs, but they come together, meaning that you have to have like 2 or 3 of them for them to be isotopes. Now, I didn't know this, and I asked the last class, and somebody looked it up, so we don't have to look it up, but somebody did look it up. Every element has an isotope.
Did someone look it up?
Somebody did. Every element has an isotope. So that's something that's interesting that I didn't know. So it's not in your notes here, but you can write that down if you want. Every element does have an isotope. Okay? And that's something that I didn't really think about beforehand. I didn't know that.
I mean, wouldn't that make sense though? Because all the neutrons can vary depending on the number of protons you have.
Yeah, I just didn't know that existed for all elements. When I was in high school, I was never told that. I just remember there were isotopes and there were common ones like carbon. But as far as it goes to all of them, I didn't know.
Wait, isotopes, they can change?
So isotopes are a result of a changing number of neutrons. So if you have the same element, but one of them has more neutrons than the other, they are isotopes of each other. It's like the same element, but it's a little bit different. So isotope. It's a result of the changing amount of neutrons, which is what you have right here. Look, atoms that have different number of neutrons are called isotopes. Okay? All right, isotopes. So after isotopes, what we want to look at next, we want to take a look and talk about the nucleus as a whole and think about its density and its size. And it's actually really intriguing. And it's gonna kind of like blow your mind in a little while. Like, wow, I can't imagine this, and it is. Okay, so just get ready. Now, yeah, it's gonna be. So, 3 facts. First, nuclei are approximately spherical. No mind blown yet. I'll tell you when it will. You'll know. Don't worry. Nuclei.
I'm so excited. He's like, just wait.
Nuclei are approximately spherical. And this is an example on the right of neutrons and protons packed together in a nucleus. And if you look at the shape, it's an approximate sphere. It's not obviously exact at all, but approximately spherical. Second, the volume of a nucleus is proportional to the total number of nucleons, or the mass in general, because remember, the mass is the nucleons. If you have a lot of neutrons and a lot of protons, you have a heavy mass. So the volume is proportional to the mass. So that means that as the volume goes up, the mass goes up. They're directly related to each other. So if I had something like the newspaper here, and I have one of them, okay? It's got a certain amount of volume, even though you can barely see it, and a certain amount of mass. Agreed? Yes?
Yeah.
No? Maybe? Yes? I hope, right? You can all see that? There's a volume, it's very little, and a mass. Now, if I take another newspaper and stack it on top, now, compared to the previous example, how much mass is there?
Double.
How much volume is there?
Double.
Double. So, nothing has changed really about it, right? So, wouldn't you say that the density of this is the same as the density of this?
Yeah.
Because the mass and volume are the same, right? And remember, density is mass over
Mass over
volume.
volume.
Very good. Mass over volume. So if the volume goes up and the mass goes up, that means that no matter what, even if you have an element with a huge nucleus and a lot of mass, it's still going to have a proportional amount. So the density of a big nucleus is the same as the density of a small nucleus. Just like if you learn about, like, in cooking. Anybody like to cook here? Okay. In certain applications of cooking, or even if you like, when you're older, if you like to learn how to like make wine or brew like beer, there's like different densities. And the densities change when you're older. And the densities change. And you look at what's called the specific gravity or density of it. Now, if you have water, no matter what, if you have a cup of water here and a cup of water here, they may have different volumes and different masses, but the density of water is the density of water. It's 1. That's what the density of water is. 1 kilogram per cubic meter. Okay? So the volume is the different part, and the mass is different, but the density is the same because it's a material. Same thing happens to apply here, and this is where your mind's going to be blown. The last part. What this means actually is that the density, first of all, this number is huge. 2.3 times 10 to the 17. If you want to compare it, think about it this way. It's 230 trillion times denser than water. So if you had, imagine a cup of water and you're holding it, right? Probably doesn't weigh that much. Multiply the weight by 230 trillion. That's what a nucleus would feel like if you had that many to make up this much space. If you took enough nuclei and put them next to each other in like a cup of water, it would be the same weight as water times 230 trillion. That's how dense a nucleus is.
I don't understand why it would be so dense though.
And that's what I went into the data class. That was the question. How is it that dense yet we're able to like exist, right?
Yeah,
Because the volume is so small, the mass is so small. You could have the most dense material in the world, but if you have such a small quantity of it, its mass must be tiny because remember, the volume and the mass are proportional. So because the volume of a nucleus is so tiny, it's minuscule, it's infinitesimally small, the mass has got to be just as small so that the density is consistent still or constant. But the crazy part is things like this. When people talk about like black holes and suns that have supernovas and collapse on themselves, the density of a black hole is even more than this. So that creates its own gravitational pull. Even though it's such a small volume, it is like, imagine taking like the earth and crushing it down to like a grain of salt. Okay? Think about that. Imagine taking the earth and just compacting it into a little grain of salt. That's like how dense it would be. It's crazy to think about this. So inside of you right now, people talk about like, you ever seen the movie? There was a movie, it was really bad. But it was called, I think, Unbreakable.
Maybe I liked it.
Unbreakable. It was like a comic with Samuel Jackson.
Yeah.
Terrible movie. But the idea was that he like couldn't get hurt and stuff. And I always think about that. When you come to like, it was really a bad movie. Yeah, it was based on a comic actually.
It was, yeah. You're right.
Which is very good. The movie, terrible.
Samuel Jackson was known for like really not nice.
Yes, exactly. And that's what.
Would that be? Well, no. Would that be because like actually?
I don't know that part, but that's what I think about like this. Think about it this way. If your atoms and the nuclei are so dense, you should be able to like withstand any force, right? You shouldn't be able to break bones. But the thing is, this further validates the fact that the nucleus is only this little portion, and the rest of it is empty space.
Yeah, but if you have so many of them on your body, I don't understand how they
Because
don't
they're
add
so
up.
small. That's the thing.
Yeah, but you just said if they're in a cup of water and they're that small, then
No. But to fill the amount of nuclei in your body would not even come close to filling a cup of water. If you put all the nuclei in your body together, side by side, they wouldn't even make up like a pinpoint. They wouldn't even make up like a grain of salt because they're so small.
So when
the
you
rest
have
of
to
your
have
body.
at least 230 trillion of them.
Yeah. Oh, you would need many more than that. Yeah.
Oh, okay. That's
You
what
have so much, believe it or not, empty space in you. You don't realize it.
So basically,
Is
Because
that
all
why
your
it's easy to
atoms.
break bones and stuff?
Well, I don't know, but like all of your atoms, you got this concentrated core and this empty space with these electrons floating around. So inside of you, even though you think like, you have material, there is a lot of emptiness. Even like, this desk here, there is so much empty space inside of all these atoms in here, but somehow, because of all these forces that are involved, they're able to stay together. And that's what we're going to talk about next, which has to do with what Emmett was asking, okay, about the forces that are acting inside of them.
Is that
Okay.
why people always like, that yo mama joke, like your mom is so fat? if she gets her own gravitational pull.
Yeah, well, that was like the Peter episode of Family Guy I brought up earlier on here. Brian starts throwing TVs at Peter because he's getting so fat that he develops his own gravitational pull and his own orbit.
Yeah, I've seen that.
And that's what's happening with a black hole. A black hole is so dense that it creates its own gravitational pull and it pulls in light. It actually is able to trap light which something else is never able to do, thus calling it a black hole. Because all the light gets pulled in and it's darkness all around.
That's pretty cool.
So how dense does something have to be to give a gravitational pull?
I don't know the answer to that, to be honest.
Can you imagine?
Everything has a gravitational pull.
But
But realistically,
Yeah, like really bad.
I mean, like something like the moon could have stuff orbiting it. Like if a small comet came by a moon, it could orbit a moon. I don't know what the actual number is. It has to do with probably the density, all the other material properties
Wouldn't
too.
that be like so painful to be like?
It's a good question. You can look it up, man. You can figure it out. If
A
you want.
black hole, yeah, that would be pretty.
You would not live.
No,
in
but I mean,
the
like, but wouldn't that be like so painful? Like, think about how dense it would be on it.
Yeah, I mean,
That freaks me out.
yeah, it'd be terrible. Anybody watch Superman or like
Yes.
Smallville? Alright. I love Smallville. Do you remember? I think it was.
You watch File XYZ too.
I think it was. I don't know if it was on Smallville.
He did not know that.
I don't know if it was on Smallville or on Superman the movie. But at one point, he takes. First of all, everybody know where diamonds come from?
Yeah.
Where?
The blood diamonds.
Not where physically. How they are created. Yeah. So it's. Yeah, so here's what happens. Side note. Side note. If you have coal and you have enough pressure on coal, because it becomes so densely packed, it creates a diamond, and that's why you see them like chipping the diamonds in the inside. So, in one of the episodes, I think it was Smallville, he takes a brick of coal and actually crushes it with his hand hard enough, because he's Superman, and creates a diamond out of it.
It's actually kryptonite.
Is it the kryptonite? No,
That's why it's called kryptonite.
I know, but the rock over it, like he doesn't feel that until the kryptonite's out.
That's in Smallville.
Oh, is that what it was?
Yeah, because the rock is.
Okay, so it was kryptonite. I was thinking I forget it was a long time, it was
that
diamond.
makes sense. Isn't kryptonite like your weakness?
That is his weakness. I don't know if that's...
Superstars.com.
Maybe. Either way, the idea of density, guys, the nucleus is extremely, extremely dense, but because it's such a small portion of the atom, it doesn't actually feel the mass as much. There's much less mass than you would ever imagine. Okay? All right. The next question is this, and before you start writing everything down, think for a second. Don't write it. How is it possible, pose this question in your mind, how is it possible that this nucleus, which consists of neutrons that are neutral, and all these protons, which are all positive, how can it stay together if we've learned that positive charges repel each other, don't they? Right? Positives repel, negatives repel, but opposites attract. So if you've got all these positive charges in the nucleus, how does it not repel each other enough that it just kind of explodes? How is it able to stay together? How can it hold itself together then?
Nicole. You're in a car.
Can the neutron like act as an electron to?
But the neutron is balanced because it's like a proton and an electron.
Is it because it's so dense? Attracted to the negative part of the neutron.
But then what's going to balance the positive part that's closer to the neutron? Follow me? If the negative of the neutron pulls the proton, then you have a positive left step. It's an imbalance of charges for sure.
I mean, I kind of agree with Nicole, because what else is there to balance the proton?
There's something else that we don't know.
There's density.
No.
Now you can read that first
The
line.
nuclear force.
Ah, good, Alan. So that's what I say now. We
Using my resources.
So, what this is the following. There's this thing called the strong force. The strong force, which is also called the nuclear force. And the nuclear force, what it does is this. It's a force that exists inside the nucleus that is independent of electric charge. Independent of electric charge. And what that means is this. Do you know how we said opposites attract with the electric force and the same signs repel? For the strong force, which is also called the nuclear force, all elements or all nucleons attract each other. All things attract each other. So for example, a neutron will attract a neutron. A neutron will attract a proton. A proton will attract a proton. Anything that's inside of a nucleus, all of these nucleons are going to attract one another. So let's say we have 8, there's 8 of each. I know you can't see it, but there's 8 of each there. The red, let's say, are protons, and the black, let's say, are neutrons. We have 8 of each. Now, the electric force that's trying to push them apart is only between the protons. Right? The protons are all positive charges, so the electric force wants to push everything apart because they're repelling. But the strong force, or the nuclear force, is a force of attraction between all of the elements. So the neutrons attract the neutrons attract the protons also attract the protons. It's this force that exists inside of the nucleus. So it counteracts the electric force. So, before we go into more detail of what else we have here, write this down. Electric force, it makes the protons repel.
But there is no electric force. Right?
There is electric force inside there is, but the nuclear force is going to overcome it, and that's what we're going to talk about.
Wait, but if there's no charge, then has there force?
Sure, there's a charge. All those protons are positively charged.
What's your saying, the electric force?
Hold on,
I'm
hon.
talking about the force, the strong force.
That's not the electric force. So the electric force causes the protons to repel each other. We talked about electric force in chapter 19. Okay? And that caused the protons to repel, which makes the atom unstable. But we know that atoms don't just, spontaneously not combust, but spontaneously explode. So there must be some other force that is keeping it stable. And that is what the strong force is doing. The strong force is not a proton repulsion force. It's an attractive force of all nucleons. It's an attractive force of all the nucleons. So, for example, the neutrons and the protons, they attract each other. They don't have to be charged. It's independent of electric charge. And this helps the atom remain stable. Now, there's a kick though. There's a little what's the word?
A glitch.
A glitch, sure, a glitch, that works. The nuclear force, okay, this strong force or nuclear force only works in a small distance. So, here's what I'm saying. And this is the tough part you have to think about.
Compact, so tight?
That's part of it, yep. Now, here's what I'm going to say, and watch, this will be easy. I have to use them in color here. So, inside of the nucleus, ready? Let's say this is a proton right here, and this is a proton down here. So take a look. This proton and this proton. They are repelling each other because of the electric force. Protons repel. These protons also repel. So do these. So do these. So do these. All the protons repel each other. But the strong force only exists in a small proximity. So there's a strong force between this proton and maybe this neutron, and this proton and this proton. But by the time you go from this proton all the way over here, there's no strong force. They're too far apart. So the nuclear force is only valid in small proximities. Which means in order for an atom to remain stable, you can never really have more protons than neutrons. Because if you start having more protons, that means that protons repel, it becomes unstable. Okay? Protons repel. If you have a ton of protons randomly throughout this process all around the outside, so say I suddenly bombarded this object with protons, right? Now look how many protons there are. All these protons are going to repel each other. But you know what? That's going to cause an electric force that's repulsive, and it's not going to help out too much with the strong force. Because it's only going to give a little more strong force on the outside where we introduce these. Because the strong force only exists around its area. So the strong force is now only a little bit more around the outside. But the electric force is present between all of them now. So the electric force becomes much larger suddenly. And the strong force becomes larger, but not by much. So it becomes unstable. So what we really want is we want the number of neutrons to be greater than the number of protons. Because if now, instead of all these things being protons, what if they were all neutrons instead? Can I get rid of them? Let's do it this way.
So we want the number of neutrons to be more than protons?
Yes, because if these are all neutrons now, take a look. I'm overwriting all of these on the outside I just put in. Now imagine they're all neutrons. Now, you don't have that many protons still. You still have the normal amount. But you have a ton more neutrons. And the more neutrons you have, the more nuclear force you have.
And the less
Repulsive force.
you have, so it doesn't have to exert as much on it.
Exactly. The repulsive force comes from the protons. So if you suddenly introduce all these neutrons into play, you're getting more of the strong force. Because the strong force, remember, is a result of the nucleons. It's responsible for holding the nucleons together. So if you suddenly put all these neutrons in here, the strong force shoots up and it holds it together. And nothing happens to the electric force. But when you put protons in a lot more, then the electric force goes up a lot. So your goal is to have a stable element, and that is by having the number of neutrons be greater than the number of protons.
But isn't the nucleons, I guess, a pair of a proton and a neutron?
But it's neutral. It's neutral either way. So it's like its own little... Imagine if you had like a mini nucleus. That would be like to me what a neutron is. It's its own little thing inside of it. And it has no net charge at all.
Okay, and so neutrons are the only things that produce, or nucleons are the only things that produce strong force in there?
Nucleons always produce strong force. So protons and neutrons both produce the strong force. So if you suddenly just introduce all these neutrons, you're getting more strong force without getting the electric force.
Okay.
So you get more stability without getting that instability from the protons. Okay? Helen?
So, what if you have like atom that loses neutrons? The strong force.
It can become unstable and it could become radioactive. And it can start to lose
so
other
that's what
things.
happens. That's how you get.
That's one of the ways you can have fission there, yeah. We're going to talk actually on Monday in our last lesson before the test. Monday, remember, is lesson. Tuesday is review. Wednesday is test next week. On Monday, we're going to talk about radioactivity. And it's another section in chapter 25. That's kind of where we're going to end. And then after that, we're going to look at fluid mechanics for a little while, for like 4 or 5 days.
Okay.
Is what Helen's talking about how you make a bomb radioactive by adding protons?
There's a lot more to it, but the idea is there, yeah. The idea is the same. You can have like a proton
How
bomb,
do you split the atom by adding
a lot of energy.
just
So-
everything?
It's energy and it's breaking the bonds within the atom. That's what you're doing. You're breaking the bonds. Those bonds have potential stored energy that they're releasing. So a hydrogen bond, a hydrogen atom is just simply a proton. That's all it is. There's no neutron. A hydrogen atom, the first element of the table, is simply one proton. That's what a hydrogen atom is. So a hydrogen bomb has to do with protons, yeah. Gab, you had a hand up or you just... No? Okay. Any other questions on this? So the idea is this. You want more neutrons than protons. So that the nuclear force goes up, but the electric force does not go up. So that the element remains stable. Sibylla, you had a question at one point. Did I answer it? Okay. Nothing else? Jens?
So just to reiterate, so for an atom to be stable, there have to be more protons than neutrons? Or neutrons?
The neutrons, remember, increase the nuclear force, which is the stability force, while not increasing the electric force. If you introduce more protons, sure, the nuclear force goes up, but the electric force goes up a lot more. So that makes it unstable.
So just more neutrons?
So more neutrons is stable. And think about that. A neutron itself is stable, isn't it? It's stable meaning it's neutral.
Yeah.
So think about that in your mind. Keep that in mind. Whereas a proton is not. Okay? All right. Take a look this weekend at a few examples. Please look at 902 numbers 3 through 5 here. 3 through 5.